Today we are going to talk about the first part of Chapter 2. So for the first part of Chapter 2, we're actually going to start with Section 3, using scientific measurements. And I want to explain the difference between the terms accuracy and precision. So accuracy refers to the closeness of measurements to the actual value, while precision refers to the closeness of a set of measurements made in the same fashion, or how close your measurements are to each other. So let's think of a bullseye. So I have a target here. Let's talk about accuracy. So let's say I take one shot and I hit the bullseye. I'm accurate. One shot can determine accuracy. Now, let's talk about a second bullseye. And let's say we're talking about 3 shots this time, and they're all there. Now, those measurements are close to each other, but they're not close to the bullseye. So these measurements are known as precise, but they are not accurate. If we have both precision and accuracy, you would see all the shots that are taken would hit the bullseye every single time. So if you're hitting the bullseye in the center, you are both accurate and precise. So these terms can be referred to in chemistry. When you're making measurements, you want to make sure that you are being accurate and precise. You're making measurements accurately by using the tools correctly, and you're making them precise by doing the same exact measurement the same way every time. So we want to be able to also analyze our errors. So I have an equation for you for percentage error right there. You'll want to copy that down. And the VA and the VE right here, you want to be able to know the difference between those two. So the accepted value right there is the known value. It's what in theory it should be. It's what you should have gotten. Okay? The experimental value is what you got in an experiment. It is your number. So when we do an experiment in class, that's your number. That's what you got by doing the experiment. In theory is what it should have been. So just as an example, let's say I did an experiment to determine the mass of chlorine, and my experimental value came out to 33 AMUs. That would be what I got for the mass of chlorine. Now I could use my periodic table to look up the accepted value, which is 35 AMUs. So the accepted value is found on a table in a chart that you'd be able to look up. The experimental is your number. Now, I want to talk about this blue paragraph at the bottom, and you might be a little confused with how it's worded, but all it's trying to tell you is how to determine if percentage error, and I really want you to look at this equation again, if the percentage error is positive or negative. So if percentage error comes out negative, that means that my experimental value is smaller than my actual value. That means when you did your experiment, your value was too small. My number is too small. And you'll want to think about that when we're writing lab reports later. That'll help you be able to analyze your errors better. Now, we can think about it from the other standpoint. If percent error comes out positive, that means my number was too big. So that means my experimental value was bigger than my actual value. So that's not always a good thing. You don't want to make more than you should have. So the best percent error that you could get is 0%. You want to be as close to 0% as you can to have a really good experiment. So let's do a sample problem with percent error. So what I like to do first when I encounter one of these word problems is I like to define my variables. So I know I'm looking for an accepted value, and I know I'm looking for an experimental value to use that equation that we just learned. So it says a student measures the mass and volume of a substance and calculates its density as 1.40 grams per milliliter. So let's analyze that sentence. A student measures the mass and volume, and the student calculates the density. So that's not a theoretical number. That is what they got by doing an experiment. So that is my experimental value, which would go right there. Now let's continue reading. The correct or accepted value of the density is 1.30 grams per milliliter. So that is my accepted value. Now I want to calculate out my percent error. So let's move that up there so I have a little bit more space. So my percent error equals my value experimental minus my value actual divided by my value actual times 100. So I want to plug those numbers in. So percent error equals 1.40 grams per milliliter minus 1.30 grams per milliliter divided by 1.30 grams per milliliter. And that whole thing, times 100. So my answer should come out. When I plug it in my calculator, I want to be really careful as well too. So I'm going to say how I would plug it in. So I would do 1.40 minus 1.30 and hit that enter button, divided by, so it says answer and then the divided symbol, 1.30, enter again, and then do times 100. And my answer should come out to 7.7%. Now, we haven't learned sig figs yet. In the future, we'd want to round for sig figs, but for right now, that's a perfectly fine answer. So I have a couple sample problems here for you to try. So go ahead, give these a try. Pause the video right now because I'm going to show you how to solve them here in a second. So pause the video, try these two problems, check to see if you get those answers, which I gave you guys in parentheses, and then when you guys come back, I'll walk you through both of them, and you should be okay from there. So here's how to solve these two problems. So the first one says, what is the percentage error for a mass measurement of 17.7 grams if the theoretical mass is 21.2 grams? So my value experimental is 17.7 grams, and my value actual is 21.2 grams. So I can plug into my percent error equation, which is VE minus VA over VA times 100. So that would be 17.7 grams minus 21.2 grams divided by 21.2 grams, and that whole thing times 100, and then I should get my answer of negative 17%. And yes, the percent symbol is a big deal because we need to know what our unit for that number is. Because all of these units, like the grams right here and the grams right here, when you subtract those, you're left with grams, but then when you divide by grams, it becomes unitless. So this just naturally turns into a percent. So the bottom, you want to do the same thing. A volume is measured experimentally, so that's my experimental value of 4.26 milliliters. And my volume actual, there we go, is 4.15 milliliters. What is the percentage error? So I'd plug into that same equation that we have right there. So I would have 4.26 milliliters minus 4.15 milliliters divided by 4.15 milliliters times 100. Plug that into my calculator. That would be 4.26 minus 4.15, enter, divided by 4.15, enter, times 100, enter, and I get 2.7%. Now, if you still have any questions after watching this video, make sure to just ask me tomorrow when you come to class.